Okay, I see it. Yeah, thank you, Rajesh. I see that recording has started. So to everyone here, good morning once again. Welcome to lecture number 3 out of my set of 4 lectures. I'm going to begin like I did last time by pointing out to those of you who may not have been checking that on the night that I deliver a lecture, I put up a set of notes. These are handwritten notes, by the way, okay? Teching takes a non-trivial amount of time, which I would have been willing to put in, but if I am not mistaken, my handwriting is fairly legible. So you have a set of handwritten notes coming up after each lecture. This is late in the night following my lecture, and this has been the case with lecture 2 as well. For those who are having difficulty seeing the contents of the Dropbox folder, I'm just about to send you a link via the chat, which I have done. And so with that, let us proceed. So I want to begin with a recap, brief recap. And I want to begin, in fact, with a recap of something that I had hinted at the somewhere towards the beginning of lecture number 2, but I had not gotten around to stating the definition formally until the tutorial that same afternoon. So let me actually put some of that up here. So last time, the one thing, what we really looked at was another case of interplay between linear algebra and last time this had been about inner products. And analysis. And the analysis part was conformal maps. Then I had, in fact, defined abstract complex structures. Right? So these abstract complex structures generalize these maps, the maps that you had seen during lecture 1, tutorial 1, and tutorial 2. So these generalize these maps.
Yes, sir.
Yes, go ahead.
Is that abstract or almost?
Oh, I guess I should say abstract, and I should add almost as well. Abstract, almost, thank you. Abstract, almost complex structures. Thank you very much. But no, I do also want the word abstract over here. The abstraction is meant to indicate that I am generalizing something specific, and these were the maps J sub D from R 2D to itself. And I must remind you, these are linear, right? And so abstract complex structures are as follows. So you've seen the definition, but I have also noticed that there are quite a few people who are missing from the tutorials. So maybe it's a good idea. And also, I think it is a good idea, since you've had a weekend in the middle, to recap what we did last time. So this is as follows. Let V be an R linear space. R linear space And our linear transformation J from V to itself is called an almost complex structure, if J satisfies the identity J squared is equal to minus of the identity transformation on the vector space V. So we have done this, and then there was sort of this important theorem, or an important proposition. I am not going to focus on this proposition very much today. The focus of today's lecture will be having fixed a vector space, looking at the collection of all possible almost complex structures and saying something about them in the large. This is one of the strategies in mathematics, right? Having defined a certain abstract concept, having seen the motivation for it, having seen the existence of a non-trivial example, we would like to study the collection of all such distinct objects. So that is the goal of today's lecture. But I'm still in recap mode. So this important proposition is actually, this is problem number 4 of the 1105 problem set. And this is important in that this gives us the motivation for why we are interested in abstract complex structures. So we have let V be an R linear space and let J from V to itself be an almost complex structure. So then I'm asking you to define the following. What I'm going to do is define what turns out to be the scalar multiplication by complex numbers of pairs of vectors coming from the same space, which has the consequence of turning the same original set with the original addition on V into a complex vector space. So I'm going to define for alpha plus I beta. So this is now a complex number. I'm going to define a new scaling or a new scalar multiplication, which I determine right in this funny way. And then I have V, and my definition is alpha. This scaling, this is a new scaling operation, is simply V scaled by alpha in the ordinary way. Now, given a vector V, JV is another vector, and I scale it in the ordinary way by beta. And I say that this is going to be my rule for all alpha beta reals and for all V coming from the original vector space. Then I take the same old space. The sum between pairs of vectors remains the same. But the scaling, I have this new scaling, which allows me to scale vectors in V by complex numbers. But thanks to this J, I land up in V itself. So this triad is a C-linear space. Right? So we saw this as an exercise. And I had asked people to work on this at home. Some of you had. Some of you were sufficiently not shy that you had a discussion with me on the key point of the proof of this. So I just want to make a remark here. The remark is that if I call this expression 1, so this is the first numbered expression of the day. So you see 1 simply has the same expression This is the same expression for vectors V coming from an abstract vector space capital V as it has the same expression for V as multiplication by C. It has the same expression as multiplication by C is given by the complex structure J sub D for vectors in R2D. So what do I mean by this? Remember, what is this J sub D actually? You see, because R2D is a real vector space, scaling by I a priori is not defined. But remember, if you have this identification between R2D and CD, that is a vector Z1, Z2, Z3, Z4, dot, 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 Z sub D in the latter space is identified with the real vector x1, y1, comma, x2, y2, comma, x3, y3, and so on and so on. Then you see what the multiplication of any Zj by I does is I times Zj is identified with the pair of real numbers minus Yj, comma, Xj. And that was the motivation behind this map. And in fact, therefore, we could say that I times the vector Z1, Z2, Z3, dot, 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 Zd, call that vector V, is actually the vector, if I multiply that by a scalar alpha plus I beta, that vector is simply alpha times V plus beta times J sub D of V, because J sub D of V is behaving like multiplication by I. And so what we do is we just transport this formula to this situation, and everything works out. Everything works out just fine. In fact, you saw that this was a part of an exercise. So now the question that arises is, what is the significance of R2D over here? When we looked at this very special example of an almost complex structure, which is J sub D, then J sub D mediated between this natural identification between R2D and CD. But there is sort of a deeper story to this, and that is what I now want to embark on. So I'm just going to step aside here for a few seconds so that people can absorb what I have done, although this is actually everything from a previous lecture. This is just a recollection. Okay, so enough of the recollection. Let's move on to today's agenda. And in today's agenda, before it is all gone, I want you to notice this statement of this result, this proposition. So these in our linear space. And I say let J from V to B, V to V be an almost complex structure. So you see, the fact that there exists an almost complex structure is a part of the hypothesis of this statement. And the conclusion of this theorem is saying something completely else rather than the existence part. It is saying something about the incorporation of the C-linear structure thanks to this. So I hope you will all see that it is a natural question to ask. Well, given an R-linear space, when does it admit almost complex structure, right? I hope you'll see that's a very natural question to ask. This is not a question whose answer has been addressed with any seriousness so far. We know, however, that the concept is not vacuous because the concept of multiplication by I, which is reformulated in terms of the linear transformation J sub D, does show that there is a rich family of real vector spaces with at least one almost complex structure on it. So the question arises, when does an R linear space admit an almost complex structure on it? Right? Now, I hope you'll agree that this is a non-trivial question, because in a lot of questions in mathematics, give us an example of A or B. Very often we come up with the answer, okay, the zero element is an example, or the identically constant function is an example, or the identity transformation is an example, and so on. That's not going to work here, because there's nothing like a trivial almost complex structure. You see, an almost complex structure, by the identity that it must satisfy as a part of its definition, is itself an invertible R linear transformation. So there's nothing non-trivial about it. And then the thing is, it must satisfy this really tight identity. So how do we answer this question? So the thing is that a complete answer is available in the finite dimensional case. Okay. And I do not want to go into the infinite dimensional case, because then we run into technicalities on the existence of a Hamel basis or not. And so questions on the foundations of mathematics are not going to be central to this and the subsequent lecture. So I'm going to make this assertion over here, but first we need some preliminaries, but we need some preliminaries. which I'm going to go through very rapidly. And I had talked about this when giving out hints to a certain problem in the tutorial last time. I am going to be a little more explicit about the hint given, but I am still either going to assume that those of you who have done some amount of multilinear algebra will be familiar with what I'm doing, and those who haven't, I'm just going to ask you to take a couple of propositions on faith, okay? So a couple of propositions to be taken on faith. So here's a proposition. Let V be a finite dimensional. Maybe I should give the dimension also. Let V be a finite dimensional vector space over the field S. So this is a statement I can make for totally general fields. Let the dimension of V be equal to n. Okay. So then there are two statements I want to make. So I'm going to introduce a gadget. So this is sometimes in the book called lambda power n of V. And elsewhere, it is also written as alt to the n of V. And this is my notation for the set of all n multilinear functionals, n multilinear functionals on V. Oh, there is a key thing that I've forgotten. I said this probably, but I did not write it. The set of all alternating n multilinear functionals on V. So what I mean by this is instead of, so think about a linear functional. A linear functional is an f-valued function or in one variable, the variable being a vector in V, with the usual linearity properties. So an n multilinear functional is a functional on V in n variables. In other words, if omega is in alt n of V, then omega is in fact a functional on the n-fold Cartesian product of V, taking values in the base field. The multilinear part is linear in each variable separately. And alternating simply means that if you swap a pair of variables, then the value changes by a -1. So, so this object, so right now I have just defined you a set. This is a one-dimensional vector space over F. So this is sort of the key basic statement. I could essentially just lead with the second statement. But somehow my conscience doesn't allow me to state this, because if I just stated what I'm about to write without any preparation, then there is no indication as to why what I'm about to write is at all true. But if you establish part one, which I'm not going to do, so for those of you who have basically studied determinants from a coordinate independent perspective, you've seen this stuff. And for those who haven't, well, I'm going to ask you to take part one on faith, and then part two simply works out because of linear algebra, because this turns out to be a really trivial vector space. It turns out to be a one-dimensional vector space. So if you take one on faith, two is kind of simple, which is given a linear transformation. So by linear, I mean, of course, with respect to the base field. Given a linear transformation T from V to itself, there exists a unique scalar d sub t. So this is a scalar determined by the linear transformation T. So this is in F, such that if I evaluate an alternating n multilinear functional, let's call it omega, on TV1, TV2, dot, dot, dot. See, there have to be n of these guys, right? So this, of course, is just a number. And this is an object which is linear in each variable separately. So it turns out that this thing is equal to omega applied to V1, V2, V3, and so on individually. And what happens is there is a scaling, there's a factor, a fudge factor, d sub t, that makes this an identity. What I mean by makes this an identity, this is true for all V1 dot, 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 Vn coming from capital V, and for all omega belonging to alt n of V. So I have this proposition, and so now let's look at what this proposition allows us to do. So suppose let S and T be two of these guys, two linear transformations. So these are two linear transformations from V to itself. Then let's look at this string of equalities. So given that S and T are linear transformations from V to itself, we can talk about their composition. This makes total sense. So what I do is I look at omega of, let's say, S composed with T acting on V1 dot, 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 acting on S composed with T acting on V sub n. Now this is equal to, so you see we can view this n tuple as S acting on the vector T of V1, S acting on the vector T of V2, S acting on the vector T of V3, and so on. So you see D sub S comes out. D sub S comes out, and I have omega applied to T V1, T V2 dot, 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 T V sub n. right? So that is by this existence statement. But aha, look here, right? So you have this expression is simplified by definition as ds times dt. So this is the multiplication in the field F times omega acting on just v1 dot 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 v sub n, right? And in fact, this for all, this part, this for which objects is what I just wrote true? Well, the same universal quantifier holds over here. Right. So let's call this is the second numbered equation of the day. But you see, by this uniqueness statement, so you see, if S and T are two linear transformations, then S composed with T is certainly a linear transformation. So you see also, okay, I think I can erase Roman 1. It's Roman 2, which is important for us at this stage. Right? But by definition, omega S composed with T acting on V1, S composed with T acting on V2, dot, 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 S composed with T acting on V sub n, this is equal to D sub S composed with T, whatever the hell this is, times omega of V1 dot, 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 V sub n. Well, for all V1 dot, 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 V sub n in capital V, and for all alternating n multilinear functionals on V, right? So you see, so over here, I have literally an identity. This is an identity because this is true, in fact, for all of these inputs and for every alternating n multilinear functional. So by comparing with this identity number 2, if I compare this with this, I have an identity ds composed with T is equal to what? Can somebody tell me?
D is
ds
composed ds into dt.
Into dt, yes. You don't say compose because d sub s and d sub t are numbers in the field F. So this is multiplication in the field. So we have this really, really, really important identity here. Right? Now, so you see, I have this unique assignment of a field element to a linear transformation, which has the property that this unique assignment for a composition is equal to the product of the individual assignments. So there is a rule in linear algebra this should remind you of. What behaves in this way?
Determinants.
Yes, who is that? Could you identify yourself? I couldn't see.
My name is Shruti, sir.
Shruti. Yes, Shruti, you are absolutely right. Thank you so much. It is the determinant. So that is going to be my third observation, which is that this d sub t generalizes so d sub t is in fact the coordinate invariant version of the determinant. D sub t generalizes determinant of A where A is now a square matrix. A is an n by n matrix, and typically when we study determinants classically, we are looking at matrices with real or complex entries, right? Although actually, this is simply because these are the two base fields in the context of which determinants are introduced, but the choice of base field doesn't have to be limited to this. So d sub t generalizes the notion of a determinant of a matrix where A is this way in the following sense, in the following way. So it doesn't just generalize it in the weak sense that the identity relating D of a composition to D of the individual linear transformations forming that composition just looks like the determinant. No, it's stronger than that. So it generalizes the determinant in the following way. And it is in the following way that if this script B n denotes the standard basis, of the Cartesian product Fn, then the determinant of the matrix A is nothing but d sub t of A, where you will now guess the way I have written it. T sub A is a certain linear transformation, and you will be able to guess what that linear transformation. So this T sub A, or sorry, T superscript A is defined by this rule, which is T superscript A is precisely that unique linear transformation whose matrix representation with respect to the standard basis is the matrix A, which is to say that T sub A acting on a vector V, if I take its coordinates with respect to the basis B sub n, then this is simply the matrix multiplication of the n by n matrix with the familiar column matrix V, which is the set of coordinates. Column of V is the set of coordinates of V with respect to the basis n. Okay. So I hope the symbolics don't scare you. What I'm simply saying is that T sub A, so what this is saying is T superscript A is the linear transformation from Fn to itself given by multiplication by a matrix multiplication by a. So in brackets, I hope the symbolics don't frighten you. I'm saying that among all n-dimensional vector spaces and linear transformations from such a space to itself, if you consider the vector space f to the n and consider the matrices, then d sub t for t equal to multiplication by a matrix specializes to something that you know, and that is this determinant. So I said specializes to, so let me highlight this. I had kept some colored chart ready. Where is it? Yes. So this should make you feel comfortable. So if you don't know what this d sub t is, then this should make you comfortable. Okay. And with this stuff, so we noted down some prelims 1 through 3. I haven't answered the question yet. So at this point, I want to pause because I am presupposing things that not everybody may necessarily know. But as I said, if you're uncomfortable with this object, think of a model of it, the representative model of it. So before we proceed, any questions? Okay, so let's carry on then. Okay, so this board tends to begin to be a bit of a mess in terms of visibility over Zoom. So let me just get rid of some of this dust. Please do bear with me. Right. All right. So here we go. So the answer to the above question is a theorem. Let V be a finite dimensional R linear space. V admits at least one almost complex structure if and only if V has, if and only if the dimension of V, and I must stress that the field here is a special one, it is R. The dimension of V is even, right? So you see, when we had looked at our first example of an almost complex structure, it had been defined on R2D, on a real vector space of even dimension. And why that was so was neither mysterious nor awkward to anybody, because the whole idea there was the ability to view a complex vector space of dimension D as a real vector space given a certain identification. And the map J sub D, under this identification, and in recognition of the fact that, strictly speaking, multiplication by I doesn't make sense on a real vector space, this J sub D encodes multiplication by I in some natural way. But in fact, even dimensionality is a necessary and sufficient condition, at least in the finite dimensional case. And this was something that Gopal was hinting at in the tutorials. So let us look at a proof of this. So I'm first going to assume that V admits an almost complex structure J. Well, so there is this identity, right? J squared is equal to minus of the identity transformation in V. So you see, so you have that D sub then D sub J squared is equal to D sub minus of the identity transformation on V. Now, of course, by the product rule, D sub J squared is nothing but D sub J, the whole thing squared. And this is equal to, this actually turns out to be equal to minus 1 to the real dimension of V. So this can actually be worked out by bare hands. So I'll simply say check. So you see, we know that given this linear transformation, D sub T, this linear transformation is minus of the identity. D sub T is uniquely determined by it. And then there is this identity, right? So what you do is, and so you should be able to see this D sub minus IV popping out. For, if it's true as an identity, it should pop out for any specific alternating n multilinear functional. So what we do is, the way we get this is, our linear transformation is very, very specific. It is something that takes V to minus V. So this is actually gotten by taking your favorite multilinear n, well, actually, I shouldn't say that. You shouldn't take your favorite n multilinear functional. You should take some appropriate non-trivial n multilinear functional, call it omega star. This is a special guy. Omega star of v1, v2, v3 dot 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 v dimension of R is equal to the same thing applied to minus of v1, minus of v2, minus of v3, minus of v4 dot dot dot. So that's how this comes about. Aha, but so you see, if you solve for this equation, you should get, depending on whether the dimension of R is odd or even. Now, if this is odd, you have -1. And then d sub j squared equals -1, its solution should be plus or minus I. But as d sub j, remember this has to belong, by definition, it has to belong to the field you have fixed, which is R in our case. But as d sub j belongs to R, it implies we have that the dimension of V is even. Right, so that is one direction. So now conversely, choose, let the dimension of V be even. And so this is equal to n for some positive integer n. Right? So this is the converse part. Now, this being finite dimensional, so if you notice, I am really going to follow the same strategy kind of blindly for how the J sub D map was defined. Okay, so why did I make that statement? I made that statement because what is the converse statement? Assuming that the dimension of V is even, I just need to produce for you at least one almost complex structure. That's all I need. So let script B, and let's write this as say W1 dot 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 W. Remember, this is now even dimensional, W2n be an ordered basis. An ordered basis on V. Okay. So now let's define. So remember, I have to produce at least one complex structure map. So define J from V to V by setting. Right, so all I have to do is to define the values of J on a basis. And if I extend R linearly, I am done. So this is what I'm going to do. So I am going to tell you how to set things. So I'm going to erase up to this point. That erases the proof of one of the directions. And I'm going to put a big bold line over here. Right, so by setting what? Okay. Setting what I'm going to do is I'm going to write J of V sub 2j minus 1. So I'm taking, oh, not V, I'm so sorry, I meant W. I'm taking, see, I have my ordered basis, so there is an ordering in it. I'm taking an even numbered element in my ordered basis. And what I'm doing is I'm mapping it to, so call it W sub 2j minus 1. I'm going to map it to W sub 2j. And I'm going to map J of W sub 2j. So this is, I'm setting this equal by definition to minus of W sub 2j minus 1. Okay. And this is, of course, so J, to be able to address every basis element in here, J just needs to go from 1 to n. J equal to 1 dot 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 n. Right. So I do the setting. So my proof is continuing from here. So define this by setting this way and extending R linearly. Okay. And well, what the hell? I mean, this computation is so simple. Let's just do it. So now for an arbitrary.
Sir,
Yes.
sir, you are defining in this way just to make the matrix of J in n block of the form 0, 1, minus 1, and 0, right?
That is, so you are saying it's going to be a block matrix, right?
Yes, yes, yes.
So so you are talking about the matrix representation of this J, correct?
Yes, yes, yes.
Absolutely right. And so it is going to be a matrix of size 2n times 2n. So what you're saying is we want to break this into 4 blocks. Is that what you said?
Yes, yes.
Excellent. Very true. Okay, can you identify yourself again? I can't see this very clearly. Who just...
Shomiran Park.
Shomiran. Okay, so Shomiran, you've kind of robbed me of the statement of my next proposition. Very good. But maybe that's a nice thing. If you are observing it, maybe there's many other people who've observed the same thing. Excellent. So another way of saying what my linear transformation is this is a linear transformation whose matrix representation with respect to this basis is a 2n by 2n matrix, which can be split into 4 blocks of n by n matrices. And as Shomiran says, these are respectively 0, the minus diagonal of one matrix, then the diagonal of one matrix, and the last block is 0. So this is exactly what this whole thing says. So let's do the computation. So you could now apply this matrix, but in this particular case, let's not do it matricially. We'll just use this basis and do a summation, okay? So for an arbitrary vector V, so you see an arbitrary vector V in our vector spaces of the form J running from 1 to 2n. So there will be these coordinates xj times wj, right? So in expanding on what Shomiran said, i.e., you could say that the coordinate matrix of V with respect to our special basis is just x1 dot 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 x sub 2n. But so we could observe what I just did here and do a matrix multiplication, but that computation will work out to exactly what I'm now about to do. So for an arbitrary vector like this, you see J squared V is going to be J applied to the summation as J runs from 1 to n. The reason I have the summation 1 to n is because what would happen is you sort of have a disparate effect depending on the value of the subscript of Wj. So you see, if this Wj is an odd subscript, then you get x sub 2j minus 1, and then you get w sub 2j. See the relationships between these two subscripts? So I am left now with dealing with the basis elements with an even subscript. So even subscripts give me a minus sign. So you get minus x sub 2j scaling the vector w sub 2j minus 1. So you have this, right? And now check what this j does. You see, j will carry this vector w sub 2j to minus of w sub 2j minus 1. And this w sub 2j minus 1 will just be carried to w sub 2j, but there is this minus sign already. So this actually turns out to be the summation as j runs from 1 to, let's again write it out, okay? So this is 1 to n. So you see this w sub 2j now gets carried to w sub 2j minus 1. But this is going to also pick up a minus sign. So you'd have a minus x sub 2j minus 1. And then minus, well, I'm going to write it this way. Plus, I would have minus x sub 2j times w sub 2j. You see, which is nothing but, it is nothing but the minus of this. It's nothing but minus of v, right? So what was my job? My job was to produce for you at least one almost complex structure. I did that. So J is an almost complex structure, right? So I produced one for you. So this is a cute theorem, right? Okay, so I'll step aside for you to absorb this for a few moments, and then I'm going to erase the board.
Sir?
Yeah.
Sir, from this theorem, we can say that if n is an odd integer, then there exists no square matrix such that whose square is minus I.
That is right.
Can we just go directly without using this stuff?
No, no. In fact, I know that any attempt to prove the formulation that you said, which is that if V is an odd dimensional vector space, then there is, or if V is, so if the statement that you're making is that if n is an odd number, there is no square matrix of size n by n whose square is minus identity. Actually, any way of proving this would be a restatement of this proof. Restatement of the first part of this proof, right? Because we can apply the determinant. If A is an square matrix of odd size, suppose A squared was equal to minus identity. On the one hand, determinant of A squared is equal to the square of determinant A. But sir, what is the determinant of minus I?
Yeah, it will be -1 if it is odd size.
Exactly.
1 if it is
Right. But you only talked about odd, right? So it'll be minus
yeah,
1.
minus.
So the square of the determinant of A is equal to -1, but the determinant has to be a real number. So this is impossible. Right? So it is basically the first part of this proof itself. So that's what I meant by, in a sense, even for the statement that you want, it boils down to just this proof, or the first half of this proof. The question that you have is only relevant to the first half of this proof.
Okay.
Does that answer your question?
Yeah, yes.
All right. So the next statement I want to make, it isn't, I wouldn't say it is a corollary to this theorem, by no means. But the fact that this theorem tells us that to admit an almost complex structure, our finite dimensional vector space has to be even dimensional. And using a part of this proof, I can actually make a technical statement, which kind of turns out to be really important. And I was debating with myself, the proof I'm going to give is just restating what I wrote out slightly differently. So I was asking myself, should I do it? Should I not do it? But from what Shumiron told me, it looks like the key idea to this proof was already presented to you. So I'm just going to say that an idea used in the above gives us the following. So here's a proposition. So this time I am going to take my vector space to be even dimensional. Let V be an R linear space of dimension to n. Let J from V to V be an almost complex structure. Then there exists an ordered basis. Ordered basis of V, call it script B, such that the matrix of J with respect to this ordered basis is a 2x2 block matrix where the blocks are 0 minus, so this one matrix, 1 sub n, I will explain it to you. 1 sub n, 0, where minus 1 sub n is just a diagonal matrix with entries, diagonal entries equal to 1. So I should probably say this is the diagonal matrix this will tell you that all except the diagonal entries are 1. This is the diagonal matrix, all of whose diagonal elements are 1. Okay. And so now I can just give you the sketch of the proof. Which is, I will just give you that basis. So remember, since the dimension of this vector space is 2n, what I do is pick n are linearly independent vectors, v1 dot v sub n. So these are linearly independent. Then set script b to be equal to v1 dot v sub n, and then j v1 dot j v sub n. So this will be my ordered basis. So you see, the key thing was in the last proof, we saw that in fact the collection v1 dot vn j v1 dot j vn are linearly independent. What do I mean by this? See, in the earlier proof, I had to just produce for you some almost complex structure. And the way I did this is by picking a certain basis. And then I was mapping the basis elements to certain specific elements that happen to be just a permutation of the original basis together with certain changes in sign. So if you just, and then I did a certain computation. So actually what I did is I actually showed that V1 through Vn, comma, negative J1, comma, dot, dot, not, negative J applied to V sub n is are linearly independent. So this follows from a computation in the last proof. Right. So you see the difficult part of this proof, of which I'm just giving a sketch, is really to prove this is linearly independent. Since we are in a finite dimensional vector space, this has 2n elements, it'll automatically, if I prove this is linearly independent, it'll automatically span. So you see, if I have a basis like this, then V sub V1 dot 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 Vn, comma, now I do away with the minus sign. So this part is trivial. If this set is linearly independent, then just changing the signs of some proper subset therein is going to be linearly independent. So this is also are linearly independent, but in particular, because of finite dimensionality, is an, well, this is an unordered basis. Right? So now so the sketch of this proof is so now everyone knows how, given a linear transformation and given an ordered basis, so this was the review problem in assignment number 1. So use the review problem number 1 to show, to compute the matrix representation of J with respect to this basis. Or another way of approaching this problem, please note, I just have a sketch, okay? So this part there's nothing conceptual about this part. If I know that this is a basis, this is just a computation. The only conceptual part was showing that this is R linearly independent. And in the previous proof, it may not seem like this is what has been proved, because in that, what we were doing was we were producing, having chosen a basis, we were producing some almost complex structure. But you see, that computation can be reversible. That particular production of an almost complex structure is reversible. So if I give you a complex structure or almost complex structure, then what that proof does is shows that this is a linearly independent set. Okay, so how am I doing on time? Okay, I thought I was going to set an alarm and I forgot to do that, but I still have some time. So let me now step aside a bit And
Sir,
yeah,
sir, it seems to me using minimal polynomial approach, we can avoid this construction.
which construction?
Means this construction of basis.
That's right. We can do that. Absolutely correct.
Because
But I
from
don't
the
have the
definition-
time. Yeah, but I don't have the time for that. So, or actually, if I had been speedier, so that was another alternative approach I was going to present. But you are absolutely right. But since I don't have the time for that, I decided that let me make use of something that you have seen that I have done kind of carefully. And all I'm saying is check that that construction is reversible. Yeah, but you are right. Okay. So I will now recall a result which I have given you for the tutorial. And you have been given not one, but 2 hints. But if you want, we can still discuss this statement in the tutorial this afternoon. But I have a little less than 10 minutes. So what I want to do is raise the question and address it in part today. The question is, how do we determine all the distinct almost complex structures, on a given Now, so this might seem like kind of a undoable problem. And if you try to approach it purely matrix theoretically, then it just becomes a huge mess. So the proof really is an interplay between matrix theoretical considerations and certain other insights. So the first step in addressing this is to realize that there are probably many distinct, almost complex structures. And so this is a theorem. The proof is actually a very few lines. And I really insist that you should be thinking about this, seeing this as a problem, a tutorial level problem. So see problem number 5 in the 1105 problem set. And let's see what this says. Let me put the precise statement, and in fact, let me go with the notation I used there. So let V be a finite dimensional or linear space and suppose J1 and J2 from V1 to its V2 itself are almost complex structures. So these are almost complex structures. Then show that, or the problem said show that. So as a theorem, this says there exists an S that is an invertible linear transform. So the short form for this is GLV. So S is an element in the general linear group, right? If you have an invertible linear transform from V2 itself, then the collection of all such form a group with respect to composition. So there exists an S in GLV such that, in fact, one almost complex structure is related to the other by conjugacy. So J2 is equal to S inverse times S inverse composed with J1 composed with S. So I have given you a hint on how to prove this. Argue, and from everything that I've done today, this argument actually becomes simpler to do. So argue why the complex dimension of those vector spaces, if you have a real vector space endowed with an almost complex structure. Remember what I had said at the beginning of today's lecture as a part of the recap. So this engenders a complex vector space with a funny scaling. So I'm going to call that vector space V sub j. So I have two almost complex structures. So argue that the dimensions of these spaces are the same. Right? So then you see what happens is, this is the key thing. Then you see, then V sub j1 and V sub j2 are C linearly isomorphic. So you see what this is saying is naively, so this is saying if I fix my favorite almost complex structure in V, then any other almost complex structure has to simply be given by the conjugacy by an element in GLV. So you could say, how do we determine all distinct almost complex structures? You could say, well, there is a bijection between the set of all distinct almost complex structures and the group GLV, but not so quick. How do you know that this conjugacy action doesn't have a non-trivial stabilizer? Okay, so that was a lot of jargon. So I will simply wrap up by stating the following point, and then I will talk about GLV and what sort of correction we must apply to it in the next lecture. So you see, the thing is, to answer the above question, we must also ask, given an almost complex structure, let's give it a name, J naught. What is the set? What is the set? So let's go with S for the moment. S for set. S sub J naught. This is the set of all capital S in GLV that does not succeed in moving this almost complex J naught, almost complex structure J naught, to a different almost complex structure according to this prescription. So in other words, this conjugacy keeps J naught fixed, right? So Rajesh, can I take about 3 more minutes? Are you there, Rajesh?
Yes, okay.
Right. So what I'm going to do is the following. So this is the question. So this is really a discussion. So what I would say is consider a J that belongs to S sub J naught. Okay. Let script B of J naught be an ordered basis such that. So remember, so there's a reason why I had stated that proposition earlier, of which I had just given a sketch. Let B of J naught be an ordered basis such that the matrix representation of J naught with respect to this special ordered basis has that block matrix form that I talked about, 0 minus in 0. And of course, the understanding is where the dimension, the real dimension of V is equal to 2n. So we take such a block matrix. And then, of course, you see, when we teach the matrix product, initially, the matrix product, the product between two matrices is just given as a formula, and we are told, okay, guys, just understand this formula, memorize it, don't make a mistake. But why is the standard product between two matrices defined the way it is? And the answer is that product represents what the matrix of a composition of two linear operators would be. So that is what I'm now going to draw on. So I'm now going to write. So you see, I've picked oh, I'm so sorry. Why did I say J? An element in this set is an arbitrary invertible linear transformation. I should say S. Sorry about that. So write S. Write down the matrix representation of S with respect to the special basis. Let's just call it A, B, C, D. Right? Then, remember, capital S is in here. So to be in here is to say that S inverse J naught S is equal to J, which is another way of writing it. An implication of this is J naught S is equal to S J naught. So you see the fun thing that's happening, where this is going. So this is now, J naught has the matrix representation -1, oh, whoops, 0, -1n, 1n, 0. What is S? A, B, C, D. This is equal to, this time you have A, B, C, D times minus times 0 minus the 1 matrix 1n 0. So you see it transforms into an extremely simple problem of multiplying 2 by 2 block matrices. And at the end of the day, everyone can do this multiplication and you get B is equal to minus C and A is equal to D. So you see, if S is in here, then the matrix representation of S with respect to this special basis must satisfy this constraint. Now, conversely, it is trivial to show that if S is invertible, and from this point on, the computation is really reversible. The only reason I said let this be in S sub J naught is because I wanted to identify a J naught, fix it, and then reference the special ordered basis. So this computation is reversible. So it's trivial to see that if S is, this is important, okay? Invertible and such that the matrix representation of S with respect to this special basis is of the form. So what does B equal to minus C and A equal to D mean? That means the top left-hand block must be the same as the bottom right-hand block. And the top right-hand block must be equal to the bottom negative of the bottom left-hand block. So you see, it's trivial that if S is invertible and this holds, then what do we have? Then, okay, so let's write down what we have. So suppose you have something like this. Then what happens is if you multiply this matrix to a block matrix that looks like this, it'll have to come out as this matrix multiplied by this special 0, -1, 1, 0 matrix, which gives us this, right? But now, see, since S is invertible, we get that also S inverse J naught S. So that's why I said this is J naught, i.e. such a matrix, such an S belongs to the set script S sub J naught. Okay, so that is the converse. And again, just so that people do not misunderstand that the material below this heavy line is a continuation of the material above, I am putting this dividing line here. Okay. Right, so that's it for the day. I am done. I haven't said that I have answered the question fully, but I have all of the ingredients to answer this. What are all the distinct, almost complex structures going to look like? But that's next time. So I will stop here. And any really quick questions, please, quick ones.
Hello, sir.
Yes.
Would take the ordered basis in that way such that the matrix